Hello and welcome to the first episode of our new series, AI Unplugged, where we look inside the AI revolution. I'm your host, Nova, and in this first episode, we're diving deep into the fascinating world of large language models, specifically how systems like ChatGPT actually work behind the scenes. Have you ever wondered how ChatGPT can write poetry 1 minute and explain quantum physics the next? Or maybe you've asked yourself, is there really a tiny person living inside my computer, frantically typing responses? Well, I'm here to pull back the curtain on these AI systems that are rapidly changing how we interact with technology. In this episode, we'll explore the transformer architecture that powers these models, how they're trained on massive datasets, the reinforcement learning techniques that refine their responses, and the very real challenges these systems face. So, whether you're a tech enthusiast or just curious about the AI revolution happening around us, this episode is for you. Let's start at the beginning. The year is 2017, and a team at Google introduces a new neural network architecture called the transformer. Now, you might be thinking of those shape-shifting robots from the movies, but these transformers transform language, not themselves. Before the transformer came along, we had other types of neural networks for language processing, mostly recurrent neural networks, or RNNs. These models processed text word by word, like you or I might read a sentence. But imagine trying to understand a complex paragraph by only looking at one word at a time, without being able to glance back at previous words. Challenging, right? The transformer changed all that with something called the self-attention mechanism. Think of it like this. When you're reading a sentence, certain words naturally grab your attention because they're relevant to understanding the meaning. The self-attention mechanism essentially does the same thing. It allows the model to give different weights of importance to different words in a sentence, all at once. For example, in the phrase, "the cat sat on the mat because it was comfortable," what does "it" refer to? You know it's the mat, not the cat, because of the context. Self-attention helps the model make these kinds of connections by considering all words in relation to each other simultaneously. This parallel processing made transformers not only more powerful at understanding language, but also more efficient to train. It's like upgrading from a single-lane country road to a multi-lane superhighway. Suddenly, you can handle much more traffic at once. So we have this incredible architecture, but how do we actually create a system like ChatGPT? The answer lies in a two-step process: pre-training and fine-tuning. During pre-training, these models are fed massive amounts of text data. We're talking hundreds of gigabytes from books, websites, articles, and more. ChatGPT's architecture has around 175 billion parameters. That's 175 billion knobs and dials that get adjusted during training. To put that in perspective, if each parameter were a letter, you could write out the entire Harry Potter series more than 30,000 times. The pre-training process uses a technique called masked language modeling. Imagine reading a sentence with certain words blacked out, and you have to guess what they are based on context. That's essentially what these models do. They predict missing words, and in the process, learn patterns of language, facts about the world, and even some reasoning abilities. You might be wondering, how does the model learn from its mistakes? Good question. During training, the model makes a prediction, compares it to the actual word, and adjusts its parameters to do better next time. This happens billions of times, gradually improving the model's accuracy. After pre-training comes fine-tuning. This is where we take our general-purpose language model and specialize it for specific tasks, like engaging in dialogue. For ChatGPT, this meant training on conversational data to make it better at responding to questions and maintaining coherent exchanges. But there's another crucial step that made ChatGPT particularly good at following instructions and avoiding harmful outputs. And that brings us to our next topic. Have you ever had a teacher who not only marked your answers as right or wrong, but gave you detailed feedback on how to improve? That's essentially what reinforcement learning from human feedback, or RLHF, does for language models. Here's how it works. First, human reviewers are shown various responses the model generates to the same query. They rank these responses based on quality, helpfulness, harmlessness, and other criteria. This human feedback is used to create a reward model that can judge how good a response is. Then, through a process called reinforcement learning, the model is trained to maximize this reward. It's like training a dog with treats. Behaviors that get rewarded are reinforced, while those that don't are discouraged. This RLHF process is crucial because it helps align the model with human values and expectations. Without it, language models might generate content that's technically coherent but unhelpful, inappropriate, or even harmful. You might be thinking, this all sounds very complex. How do they manage all this training? And you'd be right. Training these models requires enormous computational resources. The electricity used to train a single large language model could power a small town for a month. This is why only a handful of organizations with access to massive computational infrastructure can develop models like ChatGPT. Now that our model is trained, how does it actually generate text? When you type a query into ChatGPT, the system converts your text into tokens, essentially breaking down words into smaller units that the model can process. These tokens get embedded into numerical representations that capture meaning. Then comes the prediction part. Based on all its training, the model predicts the most likely next token, adds it to the sequence, and repeats the process until it generates a complete response or reaches a stopping point. But there's a crucial factor here: randomness. If the model always chose the single most probable next word, responses would be predictable and boring. Instead, it uses techniques like temperature sampling to introduce variability. Think of it like this: at a high temperature, the model might choose less obvious but still plausible words, making the text more creative and diverse. At a low temperature, it sticks closely to the most probable choices, resulting in more predictable but potentially more accurate responses. There are other techniques too, like beam search, which explores multiple possible text continuations simultaneously, or top P sampling, which selects from the most likely tokens that cover a certain probability mass. Have you ever noticed how ChatGPT sometimes gives different answers to the same question? This controlled randomness is why. It's not being inconsistent. It's exploring different ways of responding, much like a human might express the same idea in various ways. Now you might be thinking, wow, these models sound almost magical. But like any technology, they have significant limitations and challenges. Let's talk about three big ones: bias, hallucinations, and environmental impact. First, bias. LLMs learn from human-created text, and humans, unfortunately, have biases. This means models can inadvertently reproduce stereotypes, prejudices, and unfair representations found in their training data. For instance, they might associate certain professions with specific genders or make assumptions based on cultural backgrounds. Researchers are working on debiasing strategies, but it remains a complex problem with no perfect solution. Second, hallucinations. No, the models aren't seeing things that aren't there, at least not in that sense. In AI terms, hallucinations refer to when models confidently generate information that sounds plausible, but is factually incorrect. Have you ever asked ChatGPT a question and received a detailed, articulate answer that was simply wrong? That's a hallucination. This happens because these models are fundamentally pattern matchers, trained to produce plausible-sounding text, not to verify facts. They don't have a true understanding of truth or falsehood. This limitation is particularly concerning when models are used for applications requiring factual accuracy, like education or healthcare. Finally, there's the environmental impact. Training these massive models requires enormous computational resources, which translates to significant energy consumption and carbon emissions. The environmental footprint of developing a single large language model can be equivalent to the lifetime emissions of several cars. This raises important questions about sustainability as AI continues to advance. So, what does the future hold for large language models? Despite their challenges, research is advancing rapidly in several exciting directions. One area of development is enhancing contextual understanding. Current models have limits to how much context they can consider, typically a few thousand tokens. Future models might extend this context window, allowing them to process and reason about much longer documents or conversations. Another frontier is multimodal learning, integrating different types of data beyond just text. Imagine models that can understand and generate not just text, but also images, audio, and potentially even video. OpenAI's latest models are already moving in this direction, with GPT-4 demonstrating some visual understanding capabilities. Perhaps most importantly, researchers are focusing on better alignment with human values. This includes making models more truthful, reducing harmful outputs, and creating systems that can explain their reasoning or admit when they don't know something. The holy grail for many researchers is what we call artificial general intelligence, or AGI, systems that can understand, learn, and apply knowledge across a wide range of tasks at a human level. While today's LLMs still fall well short of this goal, they represent significant progress along this path. We've covered a lot of ground today, from the transformer architecture that revolutionized natural language processing to the intricate training methods that produce systems like ChatGPT. We've explored how these models generate text and discussed some of their key limitations and future directions. If there's one thing I hope you take away from this episode, it's that while these systems might seem magical, they're fundamentally pattern-matching machines, incredibly sophisticated ones, but machines nonetheless. They don't truly understand language the way humans do, but they've learned to simulate understanding in ways that are remarkably useful and sometimes eerily human-like. As these technologies continue to evolve and integrate into our lives, maintaining a balanced view of their capabilities and limitations will be crucial. They're powerful tools, but like any tools, their impact depends on how we choose to use them. I hope you've enjoyed this episode on how large language models work. If you found this interesting, please subscribe for more deep dives into the world of AI. Until next time, this is Nova signing off. Tune in our next episode when we'll be taking a look at frontier AI models. Thanks for watching.